So, yeah, not only is this a we thought about it idea, this power rule is something that has been proven. And so we talk about if y is equal to x to the nth power, and then we're going to talk, again, a lot about notation. So there's a little bit of notation that we want to consider here. We're going to say that operation, we're going to take the derivative of something with respect to x. And so that is like an operation symbol on the equation y equals x to the n. That's some notation that you're going to look at. This means we're going to take a derivative. I'm going to tell you why I'm doing that in just a minute. I'm not just doing it to try to make it look confusing. So then the operation happens, and we're going to say that becomes then the derivative of y with respect to x. So we're talking about what was our function we named, dy over dx. And then over here for the rule, that power, n, is times x to the 1 less power. So n times x is, and that's what it kind of looks like. The power rule. Oh yeah. That first question on bell work, it was just a number, wasn't it?
Yeah.
What was its derivative? You think it's always going to be true with any number?
Yeah.
Yes.
So it's just a number. That's how it works. So we call it the constant rule. If y equals a constant c, then the derivative with respect to x of y equaling c becomes the derivative of y with respect to x equals 0. When you have a constant, some c number, we're going to say that derivative is 0 every single time. And again, we've had to prove that. It's interesting and enjoyable for mathematicians. I'm not sure how the rest of us will feel about it.
How do you feel about it?
I like to do
For
it.
us just be able to skip it now then.
Oh, it's been done, so you're ready to use it?
Yeah.
That works. Okay. Guys, we're going to get a bunch of these different rules, and I want you to help keep track of these rules. So in the front cover of your book, or maybe a sheet of paper that I gave you that was laminated with the names on it. But in the front cover of your book is a listing of some of these rules. It's also on that sheet of paper. Trigs on one side, and then you've got derivatives at the top on the other side. I want you to find this constant rule, and I want you to find this power rule. Put your fingers on it and figure out which number rule it is. We can talk about that. The power rule will probably look a little bit different to you because instead of the x, they're going to use the letter u in there. And as an answer, there's going to be one more little piece on the end that we don't know about yet. We'll learn about later. But you should have the essence of n times u to the n minus 1, and then there probably is something else in there. Put your finger on those. Which is the general power rule that looks sort of like this. Which rule number is it on the front cover of your book? So this is like rule 6. What about this constant rule? Which rule is it? Rule 5? Well, there was a 1, a 2, a 3, and a 4, I guess, in front of this. Did we skip stuff? One takes into account, maybe there's a constant times our x, kind of like we did down here with this, a constant times your x. And it just said the constant times the n value, then x to the n minus 1. We sort of did it. It made sense to us. We worked on it. Number 2 is saying if I add more than one function together or subtract more than one function together, it's just the derivative of each separate function. And they're using a prime mark for u plus or minus v on
Could you
number
give a
2.
little example of that?
Number 2?
Yeah.
We did it right here. It is the monomial 8x to the 10th minus the monomial 10x to the 4th. So you take the derivative of that, ignoring whatever these things would be, and then you take the derivative of that, and so on. That's what that second rule is telling me we can do. Third rule, we'll wait a few days on.
Okay.
Fourth rule, we'll wait a few days on. Those are more specialized. We will deal with them later. So 5 and 6 are there. 7. Derivative of x is just 1. By the way, what's the slope of the line that says y equals x? Just 1. That answer to this derivative is a Copley slope. Absolute value is kind of interesting, and then, yeah, we'll do some other stuff. I want to spend a little bit more time on your just power rule and talk about some things. Okay? So we're going to do some more examples of that piece. Then a little bit later, we're going to talk about a couple of other special rules that I'm going to prove to you in a way, and then you don't ever have to prove them again. You just get to use the rule. You don't have to prove the rule. You just get to use the rule. So when we get there, I'll explain to it, and we'll do it again. Make sense about where we might be going? So let's find the derivative. So if I say f of x is equal to 9x to the 5th minus 14x squared. Find the derivative of these. Try to take the derivative of those. See what happens. Try those. Yes. You got it. Okay. Get a little space. Whoops. Come on, 2. So what did you get as your derivative for f of x?
45x to the 5th minus 28.
How many got that as their first derivative? Now, do you understand how we get there to these numbers? I take the 5 times the 9, it's going to be 45, 1 less power. I take the 2 times the 14 to get the 28, and the 1 less power. That's our power rule. So, now let's think about... Didn't like that either, did it? G of x. G prime of x is. Again, the 12 times the 2/3, that gives me 8. X to the 1 less power. 4 times 5 is 20 to the 1 less power. So that rule is still applying, correct? All right. So if we keep going, h prime of x is.
105 over 8. Oh, did I do that wrong?
It's
I
7
wrote
times
down
5.
15.
Okay. Well, that makes sense. What's the rest of it?
39 over 2x. 4x.
Do we agree? Okay. Each time we've done this, power times the number in front, and then we have 1 less power. Oh, R of x. Is that equivalent to this?
Yeah. So, maybe 4.
So let's talk this through for a second. We're taking -1 times 4. What's 1 less than -1? Negative 2 is 1 less than negative 1, correct? So does that mean then negative 1 times 4 is negative 4, but x to the positive 2 in the denominator? Do you recall that information about negative exponents? Maybe. We've got to do some more of these, right? Practice that a little bit more. Because it gets to be more fun as we go, by the way.
I did remember
All right. Any questions about what's up here so far? All right. What?
So the answer is 4x to the negative 1, or is it? That's the answer?
That's the answer.
Okay.
Yeah, that's the answer. Okay. So let's find the derivatives again. Let's see what you do with that. 3x to the 2/3 minus 6x to the negative 1/3. Let's see if you can do with that. Do we have to? Well, yeah, we kind of have to. That is y. Y equals. I can write y prime equals, I can write dy over dx equals. They do kind of mean the same thing most of the time.
Oh, you both done those.
I'm actually writing one more work step in here. I'm trying to really illustrate what happens with the exponents and also then what happens with the coefficients. So you will notice that the power rule was applied, that it's 3 times the existing power and then raised to the 1 less power. But I'm trying to show you the subtraction for that. So the derivative is, well, 3 times 2/3 is just 2. But this is 2/3 minus 1, or 2/3 minus 3/3. Becomes x to the negative 1/3. And then I have 6 times negative 1/3, which becomes 2, actually negative 2, and it's minus. So I have plus 2. And then negative 1/3 minus 3/3 is negative 4/3. So we end up getting this result, and some of us are saying, oh, I don't know if I really like the negative exponents in this problem. You remember those days in Algebra 2 where you had to have no negative exponents in the problem? Yeah.
Wait, so for these, would you also do the switch where you put the x to the 1/3 on the bottom? So that way the exponents.
Well, technically, anytime we factor out something like this and put things to the bottom, we want to factor the lowest value of the exponent present. What's the lowest value of the exponent present? Isn't negative 4/3 smaller than negative 1/3?
Yeah.
Uh-huh. So if I factor out the common factor of 2, and x to the negative 4/3 being the lowest exponent value present, will that leave me with x plus 1? And then if I really want to write this, 2 times x plus 1 over x to the 4/3 in the denominator here. That would be one way to write that, correct?
Okay, you're going to have to take a step back.
Take a step back.
Explain this.
I'm not even, I'm still on the last one. Yeah, I'm still on the last one too.
I need to figure out where the x plus 1 is from.
No.
I understand.
So we need to discuss
I still agree.
how factoring works. Right?
A little bit, yeah.
Okay. So let's do this. Yeah, I want to do it that way. One of the things that happens when we factor, guys, is we can contemplate factoring as if we are multiplying the equation by 1. And just like a lot of the other times when we multiply by 1, occasionally we think we're a little creative with the 1 that we created. So the 1 that I'm going to use to multiply this equation by is actually that common factor of 2x to the negative 4/3 over 2x to the negative 4/3. And the rules of choosing this thing are, numerically, is there a common number factor? Well, there's 2. And then for the exponent part, or the common x variable part, you're looking for the lowest exponent value present, which is the negative 4/3 over there. And so then the next part of this step is going to be, this is how I actually begin to apply this multiplication of 1. Because, it's the space. As algebra students, we know that the fraction bar is like a grouping symbol. So I can choose to group or regroup across that fraction bar. And so this is how I'm going to choose to do that. This 2x to the negative 4/3, that's the numerator value, stays right there in the numerator, stays in front of the problem. But this denominator value, I'm actually going to distribute as 1 over this denominator to each term in the problem. And so I begin to then think about x to the negative, or 2x to the negative 1/3. And I'm distributing this 2x to the negative 4/3 to that part. And then plus 2x to the negative 4/3. And I distribute also 2x to the negative 4/3 to that part. And so now I am reducing each term individually, and that's what factoring produces as a result. So I have this still sitting in front. It's still sitting there. But if I reduce these values, 2 divided by 2 is a 1, correct? And you subtract exponents because they're a common base. Negative 1/3 minus negative 4/3. Does that give you positive 3/3? Which is the same thing as just saying x to the first. And then 2 divided by 2 and x to the negative 4/3 divided by x to the negative 4/3, that should be your 1. But this is what we have to think through and process if we're actually factoring out, especially these fractional exponents. You've never seen this done before, have you?
You broke my brain.
Well, that means I'm teaching you something. This is how we actually factor. I know you were told about doing common factors and things like that, but this is really what has to happen to make that work.
Okay, will you do the negative 1/3 minus 4/3?
Yeah.
It's minus negative 4/3?
Yeah.
And that's why it's positive.
Is that what you needed? All right, I can write it out.
No, that's okay.
Okay.
Oh, well, Carolyn says right.
Are we in agreement that 2 over 2 is 1? Are we okay with that? Okay. So then basically, to simplify this, I am saying x to the negative 1/3 minus negative 4/3. When we simplify the same base with exponents, we are taking the numerator's exponent minus the denominator's exponent of that base. Was that our rule way back in Algebra 2 with exponents? And then that becomes a 1, and that becomes a 1, just plus 1. And so you simplify that little fraction, and you should get a 1 out of it as an exponent. We need to practice this a little bit more, don't we?
Okay. For the, when you multiply it as a fraction of 1, as 2x, whatever that, you chose the smallest exponent value?
Of the problem, yes.
Okay.
Sure. We started with this, and I'm asking you to take the derivative of that. So your derivative first step is here. Your intermediate step is the black part right here. But then there's that common factor that begins to show up. So let's work with it. And then we have the algebra to work with it. Really, calculus was the step from here to here, and that was it. That was the only calculus step you had in this problem. Everything else we did was algebra. All the way down. And for some of you, you're not thinking I'm done down here yet because I have that fractional exponent in the denominator we might have to rationalize that denominator and eliminate the fractions. I'm not doing that in this problem, but that's something that might happen from time to time. No?
Just do it in this column.
I think I've stretched your brains enough.